Good morning, everyone. My name is Muhammad Gyasuddin. In the previous classes, we have already discussed about 5 numerical problems based on Broglie wavelength. So today we are going to discuss about remaining numerical problem based on Broglie wavelength. Okay, our next problem is calculate Broglie wavelength associated with proton moving with velocity is equal to 1/20 times of speed of velocity of light. Okay, so this is our next problem. The statement of this question: calculate the Broglie wavelength associated with proton particle moving with velocity is equal to 1/20 times of the velocity of speed. So the given information of this question, this is clear that this is proton particle, okay, and the speed of proton particle is 1/20 times of speed of light. Okay, so the given information of this question, solution: given mass of proton particle equal 1.67 into 10 to the power minus 27 kg, and velocity of the proton particle equal 1/20 into c, and 1/20 we know that the speed of light in vacuum equal 3 into 10 to the power 8 meter per second. This is equal to 1.5 into 10 to the power 7 meter per second, and also Planck constant H equal 6.62 into 10 to the power minus 34 joule second, and lambda equal what? Okay, so for this problem we can use Broglie wave equation. We know that lambda equal h by mb. Okay, lambda equal h by mb. Lambda equal, the value of h equal 6.62 into 10 inverse 34 joule second. Yes, 6.62 into 10 to the power minus 34, and mass of proton particle equal 1.67 into 10 to the power minus 27, and speed of the proton particle equal 1.5 into 10 to the power 7. After solving this part, you will get 2.645 into 10 to the power minus 14 meter. So this is our required wavelength. Okay, this is our required wavelength. For your better understanding, I am going to repeat it once again. The statement of the question: calculate the Broglie wavelength associated with proton particle moving with velocity is equal to 1/20 times of the velocity of light. The given information of this question: particle is proton particle, okay, and the speed of proton particle is equal to 1/20 times of speed of the light in vacuum. Okay, so mass of proton particle equal 1.67 into 10 to the power minus 27 kg, and velocity equal 1/20 c. 1/20 equal c, the speed of c equal 3 into 10, speed of light 3 into 10 to the power 8 meter per second. After calculating, we will get 1.5 into 10 to the power 7 meter per second, and h is Planck constant 6.62 into 10 to the power minus 34 joule second, and lambda equal what? We know that lambda equal h by mb. So lambda equal, when all the values substituted in this equation, then we will get 2.645 into 10 to the power minus 14 meter. So this is our required wavelength. Okay, our next numerical problem is calculate the Broglie wavelength. Calculate the Broglie wavelength de Broglie wavelength associated with an alpha particle accelerated through a potential difference PD, potential difference of 0.2 kb. Okay, the statement of this question: calculate the de Broglie wavelength associated with alpha particle which accelerated through a potential difference of 0.2 kb. Okay, this is clear that this is alpha particle. Yes, this is alpha particle. Particle is alpha particle, and this is potential difference 0.2 kb. So the given information of this question, we can write given potential difference B equal 0.2 kb. We know that kilo electron volt is not SI unit of potential difference, so it should be converted in SI system. So 0.2 into 10 cube volt. Okay, so this is the potential difference which is applied on a alpha particle. And a little bit concept about alpha particle. Alpha particle means particle helium-24. This 4 is called mass number, and this is called atomic number. Okay, so atomic number, this mass number equal, we can write m alpha equal 4 times into mass of proton, and this is equal to charge equal q equal 2 into p, and this is equal to 2e. Okay, so the mass of alpha particle 4 into m into p, 4 times into mass of proton particle. Okay, so 4 into 1.67 into 10 to the power minus 27 kg. This is the mass of the alpha particle, and the charge also q equal 2p, and this is equal to 2e, that means 2 into 1.6 into 10 to the power minus 19 coulomb, and finally we can write 3.2 into 10 to the power minus 19 coulomb. Okay, and also Planck constant H equal 6.62 into 10 to the power minus 34 joule second, and lambda equal what? Okay, lambda equal what? So by using de Broglie wavelength, we know that lambda equal h by under root of 2m qb. This is the expression of de Broglie wavelength in terms of potential difference. So we can write lambda equal h by under root of 2m qb. Okay, the value of h equal 6.62 into 10 to the power minus 34, and the value of 2 into, this is mass into alpha particle, mass of alpha particle m alpha equal 4 into 1.6 into 1.67 into 10 to the power minus 27. Okay, and q, charge of alpha particle equal 3.2 into 10 to the power minus 19, and potential difference is also 0.2 into 10 cube. After solving this part, we will get 7.16 into 10 to the power minus 3 meter. So this is our required wavelength of alpha particle. The statement of this question: calculate the de Broglie wavelength associated with an alpha particle accelerated through a potential difference of 0.2 kb. Our first data is potential difference B equal 0.2 kb, and 1 kilo electron volt equal, we know that 1 kb equal 10 cube volt. Okay, 1 kilo volt equal 10 cube volt, that means 1000 volts. So 0.2 kb equal 0.2 into 10 to the power 3 volt. And mass of alpha particle equal 4 times of mass of proton. So we can write 4 into 1.67 into 10 to the minus 27 kg. So this is the total mass of the alpha particle. And then after Q alpha, that means charge of alpha particle 2 times of the charge of proton particle. So 2p equal to E electronic charge, okay, 2 into 1.6 into 10 to the minus 19. After calculating, we get 3.2 into 10 to the minus 19 coulomb, and H equals 6.62 into 10 to the minus 34 joule second, and lambda equal what? We know that lambda equal H by under root of 2 m alpha into Q alpha, okay. So when the value of all value substituted in this equation, then we will get, after solving this part, we will get 7.16 into 10 to the minus 13 meter, 10 to the power minus 13 meter. This problem we can solve alternatively. So suppose we know that alternative method lambda equal 0.20 under root of B angstrom, okay. So the value of 0.20 and under root of B, it means that 0.2 into 10 cube angstrom, and this is equal to 7.16 into 0.0271 angstrom, okay. Okay, our next problem is calculate the de Broglie wavelength associated with an average helium atom in furnace of 400 Kelvin, given KB equal 1.38 into 10 to the power minus 23 joule per Kelvin, okay. So the statement of this question: calculate the de Broglie wavelength associated with an average helium atom in furnace of 400 Kelvin, given KB, that means Boltzmann constant, equal 1.38 into 10 to the power minus 23 joule per Kelvin, okay. Now we are going to solve this problem. Solution: the given information of this question we can write. This is clear that particle is alpha particle, okay, and this is Boltzmann constant, and this is temperature, okay. So Boltzmann constant is 1.38 into 10 to the power minus 23 joule per Kelvin, and temperature T equal 400 Kelvin, and mass of alpha particle, mass of helium particle, that means alpha particle. A little bit concept about helium particle. Helium He24, this is called atomic number, this is atomic number, and this is called mass number, okay. This is mass number. So the mass of alpha particle or helium, we can write 4 times into mass of proton particle. So 4 into 1.67 into 10 to the power minus 27 kg, since mass of proton equal 1.67 into 10 to the power minus 27 kg, okay. And H, Planck constant, H equals 6.62 into 10 to the power minus 34 joule second, and lambda equal what, okay. So by using de Broglie wavelength in terms of temperature, we know that lambda equal H by under root of 3 m kBT, okay. lambda equal under root of 2 mkBT. So this is the expression of de Broglie wavelength in terms of temperature of molecule. Okay. So the value of H Planck constant 6.62 into 10 to the power minus 34, and the value of mass value of alpha particle 2 into 4 into 1.67 into 10 to the power minus 27, and Boltzmann constant is also 400, and temperature, Boltzmann constant 1.38 into 10 to the power minus 23, and temperature is also 400 Kelvin. After solving this part, we will get 6.299 into 10 to the power minus 11 meter, and finally we can write 0.629 angstrom. This is our required wavelength. For your better understanding, I am going to repeat it once again. Calculate the de Broglie wavelength associated with an average helium atom in furnace of 400 Kelvin given Kb, that means Boltzmann constant is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. This is our data from we can take from this question. So Kb Boltzmann constant 1.38 into 10 to the power minus 23 joule per Kelvin. Temperature is equal to 400 Kelvin. Okay, and mass of alpha particle, this is the 4 times of mass of proton particle. Okay, so 4 into 1.67 into 10 to the minus 27 kg, because we know that mass of proton equal 1.6 into 10 to the minus 27 kg, and H equal Planck constant, this is equal to 6.62 into 10 to the minus 34 joule second, and lambda equal what? We know that lambda equal H by under root of 2 mkBT. This is the expression of de Broglie wavelength in terms of the temperature. So when all the values substituted in this equation, then we will get, after solving this part, 0.629 angstrom. Okay, our next problem is find the de Broglie wavelength of electron accelerated through a potential difference of 182 volt. Okay, and number B part, a 1 kg object moving with speed 1 meter per second, compare their wavelength. So this question consists with 2 parts. First part is this and second part is this. Okay, now we are going to solve first part. Solution: for electron, potential difference equal 182 volt. Okay, lambda E equal what? We know that lambda equal 12.27 under root of B angstrom. Okay, 12.27 under root of B, the value of B equal 182. After solving this part, we will get this is equal to 0.91 angstrom. So this is the required wavelength of electron. Now we are going to solve second part. This is suppose A and this is B part. For object, mass of the object equal 1 kg, so mass equal 1 kg, and velocity 1 meter per second, and also Planck constant 6.62 into 10 to the power minus 34 joule second, and lambda equal what? Okay, so we can write lambda equal H by mb. This is called de Broglie wave equation, and the value of H equal 6.62 into 10 to the power minus 34, and m equal 1 kg into B equal 1 meter per second. After solving this part, 6.62 into 10 to the power minus 34 joule. Okay, 34 joule, 34 meter. Okay, 34 meter. This value we can convert in meter. Okay, So this is equal to 0.91 angstrom. This is equal to 0.91 into 10 to the power minus 10 meter. Okay. Last part, compare their wavelength. Okay, this is the wavelength of object, so we can denote O. Okay, lambda O equal 6.62 into 10 to the power minus 34 meter. Now we are going to compare their wavelength. This is equation number 1 and this is equation number 2. Now 1 divided by 2, that means lambda E divided by lambda O. Lambda E, de Broglie wavelength of electron, and lambda O, de Broglie wavelength of object. Okay, so the value of lambda E equals 0.91 into 10 to the power minus 10, and lambda O equals 6.62 into 10 to the power minus 34 meter. So after solving this part, we will get, say, something. This is our required comparison between electron and object. Okay, our last numerical problem is the wavelength of radiation emitted by a sodium atom is 5893 angstrom. Okay, what is the energy of photon? Of sodium atom, or of this radiation, and also H equal 6.62 into 10 to the power minus 34 joule second. Okay, the statement of this question: the wavelength of radiation emitted by a sodium atom 5893 angstrom. What is the energy of photon of this radiation? And H equals 6.62 into 10 to the minus 34 joule second. This is clear that this is particle is photon particle. Okay, and this is sodium atom, and this is the wavelength of the radiation. Okay, so solution: the given information of this question, lambda equal 5893 angstrom. We know that angstrom is not SI unit of wavelength, so it should be converted in SI system 5893 into 10 to the power minus 10 meter, because we know that since 1 angstrom equal 10 to the power minus 10 meter, so we can say that 5893 angstrom equal 5893 into 10 to the minus 10 meter. Okay, and H equal Planck constant 6.62 into 10 to the power minus 34 joule second, and C is 3 into 10 to the power 8 meter per second. This is the speed of light in vacuum, and what is the energy of photon? That means E equal what? Okay, so by using this formula, energy of photon, we know that E equal H nu, and H nu we can break in terms of Hc by lambda. Okay, so the value of H equal 6.62 into 10 to the power minus 34, and C equal 3 into 10 to the power 8, and the value of lambda equal 5893 into 10 to the power minus 10. After solving this part, we will get 3.375 into 10 to the power minus 19 joule. So this is our required wavelength of the photon particle. For your better understanding, I am going to repeat it once again. The wavelength of radiation emitted by the sodium atom, we know that electromagnetic radiation or light consists with a photon particle. Okay, so its wavelength is 5893 angstrom, so lambda equal 5893 angstrom, And we know that 1 angstrom equal 10 to the minus 10 meters, so we can write 5893 into 10 to the minus 10 meter. And H is also given, H equals 6.62 into 10 to the minus 34 joule second. And C, this is the speed of light in vacuum, so C equal 3 into 10 to the 8 meter per second. We are going to find out E equal what? We know that E equal h nu, this is called Planck quantum principle, E equal h nu. According to Planck quantum principle or law, E equal h nu, and E equal h nu we can break in terms of hc by lambda. When all the values substituted in this equation, then we will get 3.375 into 10 to the minus 19 joule. Thank you.